Okay, so I'm hoping this will be the last lecture that you'll have for this school year. Yay! In physics, anyway. So we're going to talk about, so last time we talked about mirrors. So now we're going to talk about refraction, which has more to do with lenses. And then you'll do a lens lab today, okay? So, so if you remember from the last lecture, refraction, this is when you have bending of light waves, okay? So how much they bend is based on something called the index of refraction. So this is a formula, and it's on your formula sheet, where n is the index of refraction. Okay, and it doesn't have units, but it always is greater than 1. Okay, it's always greater than 1. I guess it could be equal to 1, but that's weird. And c is 3 times 10 to the 8th meters per second. If you recall, right, that's the speed of light in a vacuum. Okay. And then v, this is the speed of light in a medium. Okay, so like a solid, liquid, or gas. So if you have a larger n, then that means you have a lower v, which means your medium is denser. Okay, the N of air is approximately 1. It's actually 1.0003, I believe. Let me check my constant sheet. It's on there. Yeah, okay, 0.0003. So it's almost 1, okay? And the N of water is also on your formula sheet, and it's about 1.33. Okay, so those are two that you might need for your homework, and they're also on your constant sheet. So we have this thing called Snell's law, and so you have Ni times sine theta I equals Nr times sine theta R, where the I is the incident, which means this is the incoming material. So light coming from somewhere. And the R is refraction. So this is the refracting material. Okay, so it's changing speed, therefore the object will look a little different. Okay, so my theta I is the angle of incidence. My theta R is the angle of refraction. My Ni is the incident index of refraction. And my Nr is my refracting index of refraction. Okay, and so this is Snell's law. Another way to say Snell's law would be the sine of the angle of incidence over the sine of angle of refraction is equal to the index of refraction for the refracting material over the incident index of refraction. Another way to state it would be by velocity. So the index of refraction, the refracting index of refraction over the incident index of refraction is equal to the velocity of this, well, the speed of the incident material over the speed of the refracted material, okay? So there's various ways that you can use this. Okay, so what does this look like? So for, if you're going from a low to high optical density, then your index of refraction for your incident material is less than your index of refraction for the refracted material. So that means that your refracted material, the particles are closer together, so to speak. That's what optical density means. The particles are closer together. So you have your incident light going in. This is your incident ray, and the angle it makes with just a line drawn perpendicular to the surface is your theta I. Okay. Now, if you're going from low density to high density, light slows down, so it bends towards normal. Okay, the normal is this line drawn perpendicular to the surface. That's the normal. So my theta I is here, so my refracted ray would be closer to the normal. So it's going to look more like this. So this is my refracted ray, so then this is my theta R. So going from low density to high density, your theta I is always going to be greater than your theta R. Okay, so the opposite of that must also be true. So if you're going from a higher density to a lower optical density, okay, so then your index of refraction for your incident material is going to be greater than the index of refraction for your refracted material. So if I had water here, right? So this is my angle of incidence, and this is my incident ray, okay? So what's going to happen here is light speeds up, and bends, that's not a B, and bends away from normal. Okay, so then if it bends away, that means the angle is going to be bigger. So bending away, so it's going to look more like this. So then my theta R is going to be a lot bigger than my theta I. Okay, so my theta I is smaller than my theta R. Okay, so this is an application of Snell's law. You are going to have to be able to draw this and look at pictures like this and understand and interpret them so that you can do the math for them. And of course, that's what you use to do the math for them. Okay? Okay, moving on. Okay, so some other things to note. Okay, so you have critical angles. So for a critical angle, you have this equation, right? So, so this is where you have, there's no reflection or refraction at a critical angle, okay? Because light travels along the boundary between the mediums. Okay, so this only occurs when Ni is greater than Nr. Okay, so this theta C right here, this this is your critical angle. Running into space there. That's your critical angle, okay? So, so basically what's going to happen is you have your incident and it goes to a certain point where your theta I just shines the light right on the surface instead. Well, here's the problem, is that if you're looking at Snell's law, if you're it's not an N, if your Ni sine theta I is equal to Nr sine theta R, what happens is this is a 90-degree angle. Well, sine of 90 degrees is 1, okay? So this won't work. Your Ni sine theta I is not going to equal to Nr perfectly, right? So what's going to happen is you hit that angle where the light ray is just going on the surface. So instead of it having a 90-degree angle for refraction, we just move over this Ni, right? We divide both sides by Ni. So then sine theta critical is equal to Nr over Ni. Okay. The critical angle for water is about 49 degrees. So you might encounter that in your homework too. Okay. And then we have this thing called total internal reflection. So this occurs when theta I is greater than the critical angle. So the incident angle is greater than the critical angle. So the Ni is greater than the Nr for this to happen, okay? There is no refraction. All light reflects back into the medium. Okay, so if I did this, then so here's my incident, here's my theta I. So what's going to happen is it's going to refract back. And there's my theta R. So for this, you're going to use the law of reflection. Okay, where theta I equals theta R. Okay, so you just have to remember things like that. Here's kind of just another graphic of Snell's law. That's nothing important. It's just there in case you wanted to see what it looked like. But let's see. So this is my theta I, right? So if this is my incident and this is my refracted material, it's bending away from the normal. So if it's bending away from the normal, which one has higher density, the incident material or the refracted material? I'll give you a second to think about that. So it's going to be the one with higher density is going to be your incident material. So the light is speeding up as it goes into your refracted material, so it's bending away from the normal. So if it's speeding up, then the higher density is the lower one. So this is like water and this is like air. But anyway. Okay, so that's some Snell's law. All right, and then last thing we have to do is lenses. So we talk about lenses. A lot of this is very similar to mirrors, okay? So that the math is going to be kind of the same, okay? But you had an optical devices cheat sheet, and hopefully you have printed that out by now or like looked at it or something maybe. But anyway, but your optical device's cheat sheet's kind of important here. So, okay, so this is a convex lens, right? So for a convex lens, it's called a converging lens because the image converges. So these can form real images, and they have what's called a real focal point. Okay, so that means that your focal length is positive. So what's happening is the light hits it. Okay, and so it kind of it starts to bend when it goes across. So as it comes out the other side, where the image meets, this is the positive focal point, which is on the other side of the lens from the light. Okay, so what type of image does it make? If the distance of the object is greater than the focal point, then it makes a real image, which means your image is, you have a negative DI. If the distance of the object is exactly equal to the focal point, no image appears. It's just a blur. And if the distance of the object is less than the focal point, then you get a virtual image, which means you have a positive DI. If it's a virtual image, it is always upright and magnified. If it's real, a few situations can occur. So if the distance of the object is greater than twice the focal length, then the image will be reduced. If the distance of the image is equal to 2 times the focal length, then it's the same size. So the magnification equals 1. If the distance of the object is between the focal point and twice the focal point, okay, so less than twice the focal point, but beyond the focal point, okay, then your image will be magnified. Okay, for all real images, they are going to be inverted. Okay, I have a little bit more to go. Okie dokie. Let's see. So, all right. So that's convex lenses. Concave lenses. Okay, so they are diverging. So when the light hits them, it spreads out. Okay, so woo, woo, woo. So if you kind of extrapolate, sort of, you end up with a focal point on the other side of the lens. So you end up with what's called a virtual focal point, which means you have a negative focal length. For this one, the image is always virtual. So you have a negative image distance. It is always upright. So you always have a positive image height. And it is always reduced. So your magnification is always less than 1. So your HI is always less than HO. Okay. Oops. Yeah, it's still there. You can see. Okay. So as far as math, you literally do the exact same math. You use the thin lens equation. You use the magnification equation. Same radius of curvature. So again, because I didn't change these before I printed them out and put them on the internet, that's just all of your S's should be D's, not S's. So, okay. So, and this is just kind of a picture of showing you what happens in the eye. Like if you're normal, your lens, the light goes in and looks like this. If you're nearsighted, it's like it doesn't quite go all the way back. So you have to get a lens that will diverge it so that it will send it to the back so that your eye interprets it correctly. If you're farsighted, it's like the light is going past where it's supposed to. So you need a converging lens, which will bring it a little bit closer. It'll bring it further away from the back. So that's really all. And that is the last lecture. I might add another video with some example problems, but that's about it. Do your homework, do your labs. Good luck.